Swayam Prabha. Digital India. Educated India.
Hello and welcome to the discussion sessions of Production Technology Theory and Practice course. Now, let me remind you that we started discussing in the last session the advanced machining processes or non-traditional machining processes. Okay. And I have told you in great details that why the non-traditional machining processes are required and how they come into practice. So, in gist we need to machine very hard materials which are being provided to us by the metallurgists and the material science scientists, and to machine those materials, hard materials, okay, we need to have the tool material which is even much harder than the workpiece material, and for that reason actually we have to use different other kind of energies, and then no more the direct contact between the tool and the workpiece happens. Okay. Now, in this case, in the case of the non-traditional machining, we can have actually I have shown it to you, very high accuracy, very high finish, okay, and very high production rate also in many cases. So, here if you can see, I was showing you in the last session that there is a water jet machining. Here the very fine water jet impinges the surface, okay, and it can actually make a through hole within this width. You can see the width of the workpiece shown here, all right. So, this is the kind of the grooves or the slots that the water jet can be machined by moving that water jet along with this path, okay, that can be done. Now, a fine stream of water, that is the 0.1 to 0.4 millimeter diameter. So, this diameter is 0.1 to 0.4 millimeter. Pressure, I said already that this is up to 400 megapascal high pressure, high velocity up to 900 meter per second. Stream of water is directed at the work surface to cause the cutting. Okay. Now, this kind of water jet machining process used mainly for plastic, textile, composites, tile, carpet, leather and the cardboard. So, they initially, let me tell you, the water jet machining overall was introduced to cut the cardboards, okay, wood, and that process used to be very fast, the high production rate. So, later that was tried on the nowadays it has been tried on the metal as well, and this is not very widely used, but this is successful, but mostly the water jet is used in the plastic, textile, composites, tile, carpet, leather, cardboard and so on. Here there are other examples. You can see that this is the thickness through which the water jet actually can impinge and cut. So, these are the wood, this is the wood, and that can be traversed, the nozzle can be traversed, so that the entire width can be removed. Okay. Now, here other examples, you can see that this is the some kind of a plastic material, all right, and here the shapes are very complicated, like this kind of shapes can be machined by traversing the nozzle. This is the nozzle through which the high pressure water jet is passed, and here there is also a very complicated path is being formed, as you can see that it is, this is the, by traversing the nozzle we can also have this kind of contours. Okay. Water jet cutting applications are usually automated by the computer numerically controlled or industrial robots to manipulate nozzle along the desired trajectory. Okay. Now, these are used to cut narrow slits in flat stock such as plastic, textiles, composites, float tile, carpet, leather and the cardboard, this already said. Not suitable for brittle material, for example, for glass, it cannot actually cut it because it will break and then that fracture is propagated, that and it will not be cut with a proper accuracy, and it is not it cannot be used for the glass. So, what are jet cutting advantages? That there is no crushing or burning of the work surface, okay, because there is no temperature which is involved here. Minimum material loss, of course, no environmental pollution because nothing comes out to the environment, to the atmosphere, and ease of automation. Ease of automation because we can have the computer numerically controlled and it can be programmed so that the nozzle can be moved through a very complicated path, okay, like the tool moves in case of the computer numerically controlled machines. All right. Now, introduction to the abrasive jet machining, continuing that in this process the material removal takes place due to the impingement of the fine abrasive particles. Okay. So, here we are talking about the abrasive jet machining. So, earlier we had the plain water jet, here we have the abrasive jet, instead of the water we have the abrasive jet. In this case, okay, the fine abrasive particles are used which will impinge the workpiece surface to remove that surface, okay, to remove the material from. The abrasive particles are typically of very small diameter, this is about 0.025 millimeter diameter, and the air discharges at a pressure of several atmosphere. Okay. So, here this is air is through the air, high pressure air, those particles are directed towards the workpiece, and this is the nozzle. This nozzle is at a distance of from the workpiece approximately by 0.8 millimeter. Okay. So, this is the standoff distance, as I said earlier, that standoff distance is very important. Now, the velocity, as I said, this is about very high velocity which is about 150 to 300 meter per second, and this distance, that is the nozzle diameter, is about 0.3 0.5 millimeter. Okay. Abrasive particles are very small, of 0.025 millimeter diameter. Okay. Now, here what happens that the disadvantage is that since the abrasive particles are passed through, the nozzle have to be has to be of a very hard and the wear resistant material, because the abrasive particles will wear out the nozzle and the nozzle can very quickly be worn out. So, therefore, the tip is made of the tungsten carbide, okay, or some kind of a gem. So, that is a very hard and brittle material that actually will not be easily worn out. And very often what happens is that the abrasive jet machining nozzles, they are made into two parts. Okay. So, made into two hubs and they are assembled. This is for to replace the nozzle quickly as and when it is necessary. Okay. When it is worn out to a large extent, when it cannot be used because the diameter has become much more and the jet becomes wider or the higher in diameter, as you understand, then the desired quality cannot be achieved. So, in that case the two hubs are opened and then they can be changed. So, very often there is a layer inside this, so that or there is another cylindrical surface inserted here, so that surface or bushing as we call it, that can be actually replaced. Okay. Abrasive jet machining, here the high velocity stream of gas containing the small abrasive particles, this is schematically shown here. This is the workpiece, okay. This is the gas abrasive mixture, okay. It can be air. This is the handheld nozzle assembly, and that nozzle assembly, this is kept at a certain distance between the from the workpiece, and this is the standoff distance that we set. All right. This can be actually kept at an angle that depends on what kind of material you are having. So, this angle can be calculated, at which the material removal rate is maximum, and there we have the exhaust system, so that high pressure with the gas, when it is impinging the workpiece along with the workpiece material, this can actually be sucked. Okay. So, there is a vacuum created and this material along with the abrasive can be sucked. Now, this is the gas abrasive stream which comes, and this is the material along with the abrasive material or the work material, together they can be actually going through the exhaust system. Okay. Mechanics of abrasive jet machining, as we said that this is a fracture, okay. This is a brittle fracture. Now, the abrasive particle impinges on the work surface at a high velocity, okay. And this impact causes a tiny brittle fracture here, and the following air or the gas carries away the dislodged small work particle. Okay. So, this is the wear particle, this is carried away by the flowing air, because this is coming with the gas, all right, that we said, and this can actually be also made a vacuum, and this can be sucked by the exhaust system. The process is more suitable when the work material is brittle or fragile, because it is a brittle fracture. As you can see that this abrasive grain, it impinges the surface, it makes a fracture on the surface on a tiny, of course, area, and this material is removed, okay, from the workpiece surface. This is the way the cavity is formed, okay, all over the place where it is required. All right. Now, the process parameters of abrasive jet machining, the process characteristics can be evaluated by judging the material removal rate, the geometry of the cut, okay, the roughness of the surface produced, and the rate of nozzle wear. How the process is going, how much is the material removal rate, okay, what is the geometry, like as we said that whether the suppose we have to make a hole, okay, whether it is absolutely straight hole or it is a little tapering, okay, tapering away. So, what is the quality of that? Let us say this is the workpiece and we have to make that hole, and it has to be as per directive, it has to be absolutely straight, right, but sometimes we can see that it can have a tapering, all right. So, this will actually define how the process, what is the process characteristics. The roughness of the surface produced inside the hole, what will be the roughness here. Okay. The rate of nozzle wear, the nozzle wear I already said that this has to be replaced often, because there is the abrasive particles go through, all right. So, therefore, less the nozzle wear, better will be the process characteristics, the process life is more. Okay. The major parameters which control these quantities, these are the abrasive, what is the composition of the abrasive, strength, size, mass, flow, rate, okay. These are the these are the parameters. Now, the gas, it has the composition, pressure, velocity, okay. Now, this can be regulated, pressure, velocity is normally regulated. The nozzle, that is the geometry of the nozzle, what is that material, and the distance from and inclination to the work surface, this is the stand-off distance, and at which angle the has to be directed, the nozzle has to be directed. So, these are the major parameters that will control the quality, how the machining goes, like for example, as I said that this is a drilling a hole, okay, how the hole is drilled, how well that hole is drilled. The abrasive, mainly two types of abrasives are used, aluminum oxide and the silicon carbide. Okay. These grains are of very small diameter, about 10 to 50 microns, they are readily available. Okay. This is aluminum oxide and silicon carbide also. For good wear action on the surfaces, the abrasive grains should have the sharp edges. Okay. A reuse of the abrasive powder is normally not recommended, because they are already worn out. Okay. Decrease of the cutting capacity and clogging of the nozzle orifices due to the contamination. All right. So, therefore, normally that abrasive powder which has already been used once, this is actually thrown out, because those abrasive particles, each of the grains will be worn out, okay. Their cutting ability will be less, and they will consume more power with rubbing and all, without having the proper quality of the proper accuracy and the quality of the workpiece. Okay. The mass flow rate of the abrasive particles depends on the pressure and the flow rate of the gas. Okay. So, if you see here, these are the two curves which have been made from the experimental results, and this is the qualitative curve, like this is the material removal rate on the y axis and the mixing ratio on the x axis, and here is the abrasive flow rate. Okay. There is an optimum mixing ratio, which is the mass fraction of the abrasive in the jet, okay, for which the material removal rate is maximum, as you can see here. By mixing ratio, you understand that this is the mass fraction, how much the mass of the abrasive material in the jet. Okay. So, when it is not very high, in that case of course, the material removal rate will be less, but if it is more dense, then you understand that material removal rate will be again less, because it will clog, it will not pass through very easily, because it is very dense. So, there has to be an optimum value of the mixing ratio of the mass of the abrasive grains, okay, mass fraction. Now, another curve that shows that abrasive mass flow rate, as it is more, the material removal rate increases. It is not linearly increases, but it is a non-linearly. When the mass flow rate of the abrasive increases, the material removal rate also increases. Okay. Now, of course, you understand that these are, I said that experimental curves, but this is very well understood, the physics, that flow rate will be more, so more the material removal rate. And of course, it can be shown theoretically that dependence of the MRR with the material removal rate with the abrasive flow rate is a nonlinear curve. Okay. Now, the gas, the abrasive jet machining unit normally operates at a pressure of 0.2 to 1 Newton per millimeter square. Okay. The composition of gas and a high velocity has a significant impact on the material removal rate, even if the mixing ratio is not changed. All right. So, what we say is the composition of the gas is important, and the velocity. What is the gas velocity? That has these two factors will have the effect on the material removal rate. All right. The nozzle is one of the most vital elements controlling the process characteristics. Okay. The nozzle material should be hard, as I said, because otherwise it will wear out very easily, since the abrasive particles flow through that, and the abrasive particles will also erode. Okay. The nozzle material should be hard to avoid any significant wear due to the flowing abrasive. Now, normally the tungsten carbide particles are used, tungsten carbide material is used, the average life is 12 to 30 hours, okay. Or sapphire is used. Sapphire, you understand, this is a gem, and the sapphire is very, very expensive. This is a stone or a gem, okay, and that is a very hard material, but more importantly that material is very difficult to machine. So, to make a nozzle out of sapphire itself is difficult, okay. But if it can be made, and when it is made by sapphire, the life is very high, because it is a very hard material, and you can see that life can be up to 300 hours. Okay. In comparison to tungsten carbide, also we know that tungsten carbide is very hard material, although, but the average life is not more than 12 to 30 hours. But in case of sapphire, it is about 300 hours. Okay. For a normal operation, the cross sectional area of the orifice can be either circular or rectangular, okay, and between 0.05 to 0.2 millimeter square. So, this will be the area, cross sectional area of the orifice. Orifice is through which this this goes, okay, the flow goes. Now, the nozzle tip distance, this is the standoff distance, and I already told you that the nozzle tip distance or the standoff distance, which is the distance between the workpiece and the nozzle tip, and that is very important to maintain the quality of the machined surface. Okay. The nozzle tip distance or the standoff distance is a critical parameter in the abrasive jet machining. Okay. The nozzle tip distance not only affects the material removal rate from the work surface, but also the shape and size of the cavity produced. Okay. So, this I already explained to you that material removal rate will be affected by changing the nozzle distance, nozzle tip distance. Also the quality will be affected. Okay. Quality in the sense that shape and size of the cavity that is being made. All right. As shown in the figure, so we will see this. The nozzle tip distance, when it is increasing, the velocity of the abrasive particles impinging on the work surface increases due to their acceleration. After they leave the nozzle, this increases the material removal rate. Okay. So, once again, now when we are increasing the nozzle tip distance, here it is shown here, the velocity of the abrasive particles on the work surface increases due to their acceleration, okay, after they leave the nozzle. So, therefore, what happens is that in this case, this shape that we are getting actually with an appropriate, let us say, nozzle tip distance, this shape gets deteriorated as the nozzle tip distance increases, all right, and this increases the material removal rate, of course. With a further increase in the nozzle tip distance, the velocity reduces due to the drag of the atmosphere, which initially checks the increase in MRR and then it decreases. Okay. So, this is the curve which can be drawn, that when the nozzle tip distance is increasing, initially the material removal rate increases, but after that it actually falls, stabilizes and falls. So, here we can see the entire nozzle tip distance, different nozzle tip distance is given, and for which the perfect one is made 0.75 millimeter, and if it is increasing like that, it will have the distortion. Okay. All right. Now, this is the actual photograph of the actual machined cavity profile at different nozzle tip distance. Okay. So, from A to F here, you see, starting from 2 millimeter to 20 millimeter. All right. And this is, see, what happens is that when the nozzle tip distance is less than the required one, then the energy is not sufficient. So, the cavity cannot be made properly. Then when it is increasing, the energy is increasing, energy of this impinging particles will be increasing, and then the profile will be made in a better way. At the optimum value of the nozzle tip distance, the quality of the machine surface is the best, and as it is increasing, the nozzle tip distance increasing, the energy becomes less because it is losing that in the air, and then there will be inaccuracy in the machining. That is what it is being said here. Application where the abrasive jet machining process is applied, usually performed manually by operator who directs the nozzle, okay, and put it in different, traverse it manually, normally used as a finishing process rather than cutting process. Okay. So, it is actually cutting process, mostly, as I said, it is the water jet machining that is most popularly used for cutting, but abrasive jet machining, this is used more for finishing operations, so that the ultimate surface roughness can be obtained. Okay. Applications like deburring, okay, so removing those bars, trimming and deflashing. Deflashing is that when you have the flash after the stamping operation, for example. Okay. So, that can be removed very easily by the abrasive jet machining and very effectively by abrasive jet machining. Cleaning, okay, and the polishing of the material, all right, particularly after casting, that cleaning is very important because surface is not very fine. Work materials, thin flat stock of hard brittle materials, glass, silicon, mica, ceramics, they can be used as the work material, and the abrasive jet machining can be used to remove material from them. Okay. Next process, this is called the ultrasonic machining, and the ultrasonic machining initially also I said that by name itself it says that that machining, it is the machining process where the ultrasonic frequency is used, and the ultrasonic frequency, you know that this is a very high frequency, it can be up to 25 kilohertz. Okay. The basic mechanism, basic USM, that is the ultrasonic machining process, involves a tool, okay, made of a ductile and the tough material. So, here you can see that in the diagram, line diagram, you can see that this is the tool. So, this tool is made of a ductile and a tough material, okay, vibrating with a low amplitude and very high frequency. Frequencies here it is set up to 220, but it can go up to 25 kilohertz also. So, that amplitude is here, as you can see that it is 15 to 20 micron. So, this is a low amplitude and very high frequency, 20-25 kilohertz. Okay. And a continuous flow of an abrasive slurry. So, there is a nozzle, through that the abrasive slurry is, that is the stream of abrasive material is passed through and the tool vibrates. Okay. And this abrasive stream of abrasive material is passed through the gap between the tool and the workpiece, which is the stand off distance. Okay. The stand off distance we have already discussed. The tool is gradually fed with a uniform force towards the workpiece, because the workpiece material is removed here and the stand off distance is changing. So, to maintain that stand off distance, the tool is given a feed force, and depending on how much workpiece is being removed, so accordingly the tool moves towards the workpiece with a particular feed. Okay. And this arrow shows that this is the way the tool vibrates with a very low frequency. Right. It cannot be seen even with the open eyes, with normal eyes. Okay. And it has a very high frequency also, 220-25 kilohertz. Okay. Now, the impact of the hard abrasive grains fractures the hard and brittle work material. This work material is hard and brittle, resulting in the removal of the work material in the form of small wear particles, and these wear particles can be taken away by suction. The tool material, being tough and ductile, wears out at a much slower rate than the workpiece. Okay. Because as you understand that these were abrasive materials or abrasive particles, they also impinge the tool, but it will impinge after it gets rebounds from the workpiece actually. All right. So, therefore, the tool, the frequency and the amplitude given by the tool, this is imparted on each of these particles, and those particles then with that frequency it actually, and with that amplitude it impinges the surface, and it is a brittle surface, okay, and hard material. So, this will actually break, or it will fracture, it will have a brittle fracture, and that fractured material piece will be removed from the surface. So, mechanics of ultrasonic machining, the reasons for material removal in an ultrasonic machining processes are believed to be. So, these are the mechanics, 4 mechanics. One is the hammering of the abrasive particles on the work surface by the tool. Okay. So, here we have the abrasive particles, this is being hammered because the tool is imparting the vibration, certain vibration to each of these particles. Okay, that is one. The impact of free abrasive particles on the work surface, that is the impact. The erosion due to cavitation, okay, and this cavitation by means that this is being cavitated, this each particle is cavitated in the space here. So, this actually creates the erosion of the material. The chemical action associated with the fluid used. So, these are the different reasons that are to some extent or to a large extent one of them or few of them together, they can be actually applied as the mechanics of ultrasonic machining. That is what it is said here. Okay. Ultrasonic machining process, the volume of work material removed, this is Q, let us say, this will be proportional to basically three factors. One is the volume of the work material removal per impact, this is let us say V. Okay. Number of particles making the impact per cycle, of course, more the number, more will be the material removal rate, all right, material removal Q. Volume of the workpiece material removal per impact, if it is more, then the material removal rate will be more, and if the frequency is more, so in that case the material removal rate will be more. So, therefore, the volume of work material removal rate depends on the volume of the work material removal per impact, okay, number of particles and the frequency. This is the diagram. We will not go into very details, but this diagram actually is necessary to understand for assessing the how much work material will be removed. So, to simulate, let us say, meaning that if you do not have the process and you want to actually have the maximum material removal rate or an optimum material removal rate or the optimum parameters, in that case you can go for the simulation. For that you find out what is the tool position, different tool positions, that is the mean position when the tool touches the grain. Okay, that means in between the tool and this, in the standoff distance there will be abrasive grains. So, when it is touching and the tool, bottom position will be here of the tool. So, then it will be actually useful for that. So, how much time required for this and so on. Now, the position A, this position indicates the instant the tool face touches the abrasive grain, the period of movement from A to B, then it is moving along with this to the B, okay, and by that you understand that there will be already a fracture, because it is moving from A to B. First it comes and touches that grain, then it moves from A to B. So, by that this will also move. Okay. So, this represents the impact A to B when the tool is moving along with the abrasive grain. So, then it will have an impact. The indentations caused by the grain on the tool and the work surface at the extreme bottom position here, okay, of the tool from the position A to position B is H. So, this position from here to here, this is the bottom position, this is H. This will be the indentation. Okay. So, this is what it is said, this is the H. So, this much indentation is made, all right, this much indentation is made when the tool is moving from A to B, and this is the bottom position. Okay. That is what it is said, and let us say this is H. So, if we now plot the material removal rate and the feed force, okay, you will get a curve like that. Now, what happens is that theoretically as you understand that as the feed force is increasing, the more material will be removed, okay, because it is the volume of each particle will be more in that case, and according to this equation, if the V is more, in that case the Q, which is the material removal rate, will be more. So, therefore, it will actually grow like that, and theoretically it will be that when the feed force is increasing, the material removal rate grows, all right. But actually what happens, that when the feed force is increasing, that means more force is required to move the particle. Here for example, we said that the particle, the tool is touching the grain and then it is moving here. So, more feed force is required to move that, so that material removal rate grows. But as it is increasing beyond certain level, the force is so high on the grain that grain may crash. Okay. In that case, its impact capability is decreasing, that means it will not have the proper impact and it will not have the removal of the material. In that case, this is the curve which is happening actually. So, MRR increases with increasing the feed force, but after certain critical feed force, let us say in this case it is here somewhere, all right, it decreases because the abrasive grains get crushed under the heavy load, because the feed force is increasing too high, has become too high. Okay. All right. And now the other process parameters in the abrasive machining processes, these are the frequency, amplitude, static loading, which is the feed force, hardness ratio of the tool and the workpiece, grain size, concentration of the abrasive in the slurry, and so on. And these are the curves which shows actually that what is the relationship between the frequency, amplitude and the material removal rate. Okay. Here is the same thing, that this is the actual, I already told you the reason, that this is the actual curve, and the theoretically it should have been a straight line. Okay. And as the frequency increasing, so each of these curves, if you see overall, first of all, as the amplitude is increasing, material removal rate is increasing. Okay. But more material removal rate will be, we will get as the frequency is increasing. Here the frequency is less than here, here it is, in this, at this curve is made with the higher frequency than this and this. Okay. So, here is the same thing written here in the text, that with an increase in the frequency, okay, of the tool head, the material removal rate should increase proportionally, theoretically. However, there is a slight variation in the material removal rate with the frequency. Okay. I explained it to you the reason earlier also. When the amplitude of the vibration increases in the second curve, the material removal rate is expected to increase. The actual nature of the variation is shown in figure B. This is the actual nature. All right. There is some discrepancy in the actual values again. Okay. So, this actually is not exactly straight line, but you can see that here and here it is like this. This arises from the fact that we calculate the duration of penetration delta t by considering the average velocity and not the instantaneous velocity. Okay. That is why it is actually not a straight line, but it is a very small inclination, and this can be actually in some cases it is not for high frequency. For example, here this is almost straight line, but here it is a discrepancy because the frequency is low. Okay. Now, this already I have explained to you. This is that with the diameter, MRR should also rise proportionally with the mean grain diameter. Okay. And this is similar to this is the feed force and the MRR. So, reason is the same, that they get crushed. Okay. Crushing tendency increases. Now, the concentration of the abrasive directly controls the number of grains producing impact per cycle. Okay, you understand that by concentration we mean that how much grain is per unit volume of the fluid or the jet. MRR is proportional to C to the power 1 by 4, okay, concentration to the power 1 by 4. So, after C rises to 30%, MRR increases is not very fast. This is almost stabilizes, you can see that, and this is made for, this is the abrasive concentration percentage C. So, this is made for two different abrasive materials, boron carbide and the silicon carbide, and the material removal rate for boron carbide will be more than the silicon carbide, as you can see here. Okay. And this stabilizes because this is the relationship. This is also of course empirical relationship, that the MRR is proportional to C by proportional to C with the C by 1 by 4, C to the power 1 by 4. Okay. So, therefore, it stabilizes after that, after some time. Now, concentration of that is what it is being already explained here. Now, apart from the process parameters, some physical properties, for example, the viscosity, the curve shown here, that as the viscosity is increasing, what happens to the relative material removal rate, okay, of the fluid, viscosity of the fluid we mean to say, used for the slurry also affects the MRR. Experiments show that material removal rate drops as the viscosity increases. Okay. As the viscosity is increasing, so you understand that there of course, the fluidity will be more, so therefore, material removal rate will be less. All right. Although the material removal rate is a very important consideration for judging the ultrasonic machining, but so is the surface finish. in case of this. Okay, we are talking about the in case of the ultrasonic machining, that the material removal rate is important consideration, but the surface finish also is similarly important along with the material. Material removal rate gives you the production rate mostly, okay, and surface roughness, because these are the precise parts which are being made by the ultrasonic machining. Therefore, the surface roughness is very important. Dependence of the surface finish on the grain size, let us say for tungsten carbide and the glass, okay, material. Mean grain diameter we have taken as a micron from 50 to 150 experimentally, and this is how the curve goes. The figure shows that the surface finish is more sensitive to grain size in case of glass, okay, because in case of tungsten carbide you can see the curve is not very steep. So, therefore, it is more sensitive in case of glass, which is softer than the tungsten carbide. That is why this happens in this way. Okay. This is because in case of a harder material, the size of the fragments dislodged through a brittle fracture does not depend much on the size of the impacting particles. Okay. Let me explain it to you once more. What happens, we are saying that this glass is more effective, okay, on this, showing this. This is because in case of a harder material, the size of the fragments dislodged through a brittle fracture is independent of the size of the impacting particles, okay. Whether it is a bigger or it is a smaller, it does not matter, it does not impact. Okay. Now, the unit in that ultrasonic machining is the following. This is the basic machine body. Okay. Here we have the slurry pump and the slurry tank, all right, from where it is supplied to the machining zone, where we have the work on the work table, okay, and the tool here. The tool is mounted on the acoustic head, and acoustic head is actually like this, that it is something like this. Okay. It actually goes in like this, and this is the tool. Okay. Well, I mean, it is not, it is of course not to scale, and it is, you understand that this is it is maintained, the axis is maintained. Now, this is done in this shape to concentrate the vibration, okay. And you understand that this is vibrating at a very high frequency and low amplitude, and this is a concentrator, therefore, it is called the concentrator. This is not shown here, this is simply said this is tool, but this is the concentrator and this is the tool. So, tool is mounted at the end of the concentrator, okay, and the workpiece is here, okay. This is the workpiece. Between the workpiece and the tool there has to be a stand-off distance, okay. So, this is also not shown here, and in the stand-off distance, of course, we have the, through this we have the abrasive slurry. So, this is the diagram, all right. Now, the main units of an ultrasonic machining unit, ultrasonic machine shown here in the figure, it consists of the following components: the acoustic head, as I said, the feeding unit, the tool, the abrasive slurry, and the pump unit, and the body and with the work table. Okay. This I have already shown it to you. So, this is here in the head there is a feed mechanism, because once again the tool has to be forwarded towards the workpiece, because the material is being removed and the distance between the tool and the workpiece is increasing. So, that is the stand-off distance which has to be made constant, which cannot be changed. So, to make that stand-off distance constant, the tool has to be forwarded towards the workpiece as the workpiece is removed or is machined. So, this is the position indicator. That indicator will actually show you that what is the tool and the workpiece material distance, okay, or the stand-off distance. Acoustic head, these are the type of the concentrators that I was trying to show it to you. So, this can be a conical, very popularly used types of concentrators are the conical, it can be a stepped concentrator or it can be an exponential concentrator. This is called the exponential concentrator, not the conical. So, conical and the exponential, they are more popularly used. I was trying to show you in a diagram the exponential one. Well, the acoustic head's function, here is the details of the acoustic head. This is the tool, this is the concentrator, here it is the conical concentrator. Okay. So, since it is the high frequency, here as I said that the frequency can be 20-25 kilohertz. Okay. So, at that high frequency the temperature produced will be very high. All right. So, this is generated by means of a generator and this is the transformer. This transformer helps in producing the required vibration that is here required here. So, this is concentrated and it actually is imparted to the tool. All right. Now, since high temperature is produced, there will be a cooling fluid here. This is to cool the surrounding of this concentrator and this is circulated. So, this is the purpose of the cooling fluid. So, the function of this acoustic head is to produce a vibration in the tool. Okay. It consists of a generator for supplying a high frequency electric current through this, a transducer to convert this into a mechanical motion in the form of high frequency vibration, a holder to hold the head of the, this is holder and all, it is inside, a concentrator to mechanically amplify the vibration while transmitting to the tool, this is the concentrator. Okay. And these are the types of concentrators as I was telling you. Okay. Now, the abrasive slurry, the most common abrasives are the boron carbide, silicon carbide, corundum, which is the aluminum oxide, diamond, and the boron silicarbide. Okay. So, these are the more popularly used abrasives. B4C boron carbide is the best and most efficient among the rest, but it is more expensive of course. Okay. Now, the silicon carbide is used on glass, germanium and most ceramics, because the ceramics are brittle materials, by the way, glass is brittle material, they are very hard materials. Okay. So, this is for that silicon carbide is quite suitable. Cutting time with silicon carbide is about 20 to 40% more than that with the boron carbide. Okay. It takes more time. Now, the diamond dust is used only for cutting diamond and the rubies. Okay. That is the slurry that is used here. So, diamond slurry is used in the form of a diamond dust, but this you understand that this can be used for very, because it is expensive. So, for using and exclusively for diamond, rubies, okay, where the high precision is required and the material is very hard and very brittle. Okay. Water is the most commonly used fluid, although other fluids, other liquids such as benzene, glycerol and the oils, these are also used. So, this we mean to say that we mix the water or the benzene, glycerol, oil with these powders. Okay. Either it is a boron carbide powder or it is a silicon carbide powder or it is the diamond powder. All right. Now, this is the summary, this you can see. So, I am not going through this, I have already told this. All right. So, this is listed, tabulated. Now, here the look at these abrasives, we have said mechanism, mechanics of material removal, we said brittle fracture, abrasives we said, vibration we said. Tool material is soft steel, okay, and material removal rate per tool wear rate is about 1.5 for tungsten carbide workpiece, okay, and it is more for the glass workpiece, because it fractures and makes a brittle fracture of bigger pieces. This gap, that is the standoff distance, Critical parameters, we already said that. Material application, it is a metals and alloys, particularly hard and brittle material. Okay. Semiconductors, non-metals, for example, glass and ceramics. Shape application is the round and irregular holes, impressions. Okay. Limitations, they are very low material removal rate. Tool wear, because it is a high frequency this thing, the abrasives, and therefore, the tool wears out. Depth of holes and cavities small, because if you go to higher depth, the energy is not sufficient. So, that means you have to increase the amplitude and the frequency. All right. Next in line of the unconventional machining, this is the electrochemical machining, and electrochemical machining is one of the most popular unconventional machining processes. Okay. The process is actually the reverse of electroplating with some modification. This I already mentioned in the beginning when I was telling about the introduction of the processes. Okay. It is based on the principle of electrolysis. Electrolysis process we are all familiar with, and the basis is the principle is of electrolysis. In a metal, electricity is conducted by free electrons, okay? But in a solution, the conduction of electricity is achieved through the movement of ions. Okay? By solution we mean to say, suppose some kind of an electrolyte, okay? There the movement of ions take place and the electricity is passed through this by the movement of ions. Thus, the flow of current through an electrolyte is always accompanied by the movement of matter. Okay. In the matter means ions we are talking about. Okay. In the electrochemical machining process, the workpiece is connected to a positive electrode and the tool is to the negative. So, let us say in this schematic diagram, we have the tool here, the work here, tool has been made as a negative and the work has been made as a positive, you can see from this. Okay. Now, here this is tool is being advanced towards the workpiece, okay, and if the shape of the tool is like this, it is conformed on the workpiece surface, and you can see that with a certain distance achieved. So, the machining starts, okay, when the voltage is passed through the work and the tool through the electrolyte. This is both workpiece and the tool are dipped in the electrolyte, and the machining starts when the standoff distance between the tool and the workpiece is certain. Okay. Now, this will be the steady state of electrochemical machining, and the distance as the workpiece wears out more because of the tool, I mean the material removal becomes more, then the distance is becoming more. So, the tool has to advance further. Okay. So, this is the schematic principle of electrochemical machining. Once again, the workpiece you can see is connected to the positive terminal, okay, and the tool is connected to the negative terminal. Okay. All right. Now, here is the electrochemistry of the electrochemical machining. The reaction at the anode, okay, reaction at the anode means we mean to say that it is here, this is the anode, okay, and this is the cathode, okay, tool is cathode. So, let us say this is the copper material. So, in that ferrous material, in that case the ferrous in the anode will be like this, that ferrous 2 ions will be created and 2 electrons will be created. Okay. Now, the electrode metal ferrous, let us say, dissolves because this is ion is maintained, ion is created, leaving 2 electrons, that would be in the anode, okay, in the workpiece material. So, let us identify this. For example, here we will say that the work is the ferrous material, okay, and this is work is the anode, okay, this is the anode. This tool is cathode, okay, of some material. So, we will come to that because it is immaterial tool. Actually we what we want is to remove the material from the anode, from the workpiece. Okay. So, in the cathode what happens, the electrode metal in the cathode the 2H2O, because there is water plus this 2 electron taken from the anode, this will create hydrogen gas and the 2 hydroxyl ion at the cathode. Okay. That is what it is written, that the positive metal ions tend to move towards the cathode and the negative hydroxyl ions are attracted towards the anode. Okay. The positive metal ions combine with the hydroxyl, okay, with the negatively charged hydroxyl ions, and they will form the ferrous hydroxide. Okay. That ferrous hydroxide will precipitate. All right. So, the anode dissolves in the terms of the ferrous ions and finally, the ferrous hydroxide, okay, as you can see here. And the tool, whatever is the material of the tool, that is what I said, nothing happens to the tool which is in the cathode. Okay. So, ferrous is dissolved, but nothing happens to the tool, because at the cathode this is what happens, that hydrogen gas is evolved from the electrolyte that we have it there, where the both tool and the workpiece are dipped, all right, and it ultimately the ferrous ions which are produced at the anode, it will be precipitated as the ferrous hydroxide. So, the anode dissolves and the hydrogen gas is generated at the cathode, leaving the cathode shape unchanged. So, this is one of the biggest advantage of the electrochemical machining, that here the tool does not wear out, nothing happens to the tool. So, we can use the tool let us say copper material. Okay. So, that can be used for a very long time, because there is almost or there is no wear of the tool. So, this is one of the advantages of the process. Now, here the electrochemical machining is schematically shown, that this is the tool which is the cathode and workpiece is anode. So, the gap between the tool and the workpiece material, when it is maintained at a proper level, which is the standoff distance, then as you can see the workpiece is being removed. So, this much material is removed and the workpiece shape is becoming the same as the shape of the tool. So, that means this is conformed, the shape of the tool is conformed to the workpiece, all right. And of course, there should be a movement of the tool towards the workpiece, because the distance, the standoff distance is increasing. So, this is the schematic diagram of the electrochemical machining, which is showing the principle. I will once again repeat that electrochemical machining is one of the most popular processes, where mechanism of the material removal is by electrochemical dissolution. And as we have seen that in the electrochemical machining, the workpiece is removed, material is removed from the workpiece and nothing happens to the tool material. So, if the tool material is even the soft material, in that case that it can be used for longer period, because the tool does not wear out, okay, because at the cathode only the hydrogen gas is evolved. So, as I showed it to you here, if you see this is the process which happens. So, the ultimately the material is removed from the anode, which is the workpiece, and at the cathode nothing happens but the hydrogen gas is evolved. So, rest of the material in this subchapter of the electrochemical machining I will discuss in the next session of discussion. Thank you for your attention.